So titrations. I don't know. I'm somewhat of a recent coffee drinker, and the wife just got a job teaching biology, so I don't think she'd have access to, how do you pronounce that, botulinum or something? But I'm told it's the most toxic substance known to man. 90 nanograms is all you need to kill somebody. So she wants to know if she has enough. And this is kind of scary. I mean, terrorism is, you don't need you can do a lot with very cheap stuff. And this is just one example. I mean, all you need is this little titration setup. And you pretty much just set your unknown that you're analyzing in there, right? Because maybe 90 it kills you, but it's also below the detection limit of forensic science Joe dude in the forensic science laboratory San Antonio, right? You want to make sure it's below a certain level so you can't get caught. So you do your titration setup, right? Stop when it changes color, plot out your data, do the calculations, and have at it, right? So here's an example of a plot. Does it look like they screwed up on it? Right? Because when we think of titration curves and plotting them out, what do they usually look like? Do you remember doing this? I think you've done it in general chemistry. What do they look like? Do you remember this? All right, especially if you're doing pH. It starts out, boom, 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 boom. Then all of a sudden the pH might be going up a little bit, but not very much. Then all of a sudden it skyrockets, and then it flattens out again. Kind of goes up slowly, right? That's usually what they look like. But here it looks like you have two big bumps. Did they screw up? Or, so I guess it looks like, to tell you, it looks like this when only one reaction takes place. Maybe you're titrating NaOH and HCl. But how could you get two reactions to titrate? How could you get two reactions to go on? NaOH and not a monoprotic acid, but a, what do you call it when you have two acidic hydrogens? Diprotic. What's an example of a diprotic acid? You know one of them, it's strong. H2SO4. Right? First, you're going to get the first acidic hydrogen to react. There's one of them. Right? The most acidic hydrogen will react first, and then boom, the next one will react. A lot of things in nature are diprotic, and a lot of things going on inside your body and cells. There's most everything's diprotic or triprotic, and you just keep getting more and more and more. Okay, but so that's not screwed up. So titrations. Just what is a volumetric analysis? That's what the young lady did to try to kill her husband. Now, let's do some terminology first. Adrian, the thing that we're after, we always called it the what? Started with an A. And we want to know how much, like in this case, she was after this botulinum. That was her what? We called it her analyte. That's her analyte, right? So what you're after, trying to figure out how much analyte there is all the time. Where is the analyte? Nyla, in a volumetric analysis, where is the analyte? Yeah, that's what's in the beaker, right? Your analyte's in here. Okay. What's the chem speak, Casey, for what's in the burette then? So close. Titrant. Titrant. All right. So there's the chem speak, pretty much, for volumetric analysis. There's some more words we're going to talk about, but let's just try this. Okay, I have a setup. Okay, had a setup. Okay, So I want to titrate blank mils of an unknown concentration of HNO3. Okay, so I measured out while you guys are taking the lab, or taking the quiz, and that looks like about how many mils? Around 10. All right, so let's put in a 10 there. Okay. So the question really comes down to 10 mils of this unknown molar concentration of this nitric acid is question mark mils of 2.1 molar NaOH. Because where's my NaOH? Here it is. Okay. So my, what did I do with my, oh, I didn't dump it in there. So the analyte goes in the beaker, right? Okay. Done. Okay. Analyte goes in the beaker. Titrant goes up there. Whoop, wrong one. That would be a mess, huh? Okay. Oh. John, get up here. Here, let me. You take this. I'll hold it. I'll get it out of there. Can you? You can reach that, right? Get it out of the way.
Let's do it.
Oh, I don't know. Oh, make sure this is closed first. Remember doing that? Very good. Just dump a bunch in there. That's good. That should be plenty. Okay. Thank you, sir. And while you're there, though, oh, I can reach this one, right? Oh, get those bubbles out of there. Well, you know, you take your time and stuff. I'd say it's about 13.8. 13.8 is the initial on the barrette. 13.8. That's our initial on the barrette. Okay. Now, a couple problems here. Remember this? You want to make sure that's filled with it, filled with the NaOH, so we should probably dump some out. So our 13.8 is going to be wrong. Get all the air and bubbles out of there. I'm going to have to read it again. It's about 14.4. So I got all the air out of here, right? You have to get all the air out. Okay, 14.4 is initial. Now, what do I need to do? I'm going to keep adding this liquid to here, but how do I know when to quit? Indicator, right? That's the first one, indicator. So what's the big deal about an indicator? It changes color, but when? How does it know to change color? How does it know? There's no brain going on here. How does it know that's supposed to change color? It goes with pH. All indicators, right? They're all weak acids. But their conjugate acid and their conjugate base are different. There's the C. They're different colors. The conjugate acid and the conjugate base are different colors. That's all. So phenolphthalein one of them. Okay, and put a couple drops in there. Okay. Now it's going to be kind of hard to see, like you can't even see it back there, right? And plus I probably left some in here, some of my analyte. Can I do this? This is just my DI water. Can I rinse this out and dump it in there? It's just water. I can add anything I want, and as long as whatever I'm adding doesn't react with my technical word, titrant. As long as it doesn't react, it won't. So yeah, you probably should, because we're doing anal chemistry, right? You don't want to miss anything. And okay, so I could do that. I'd rinse it a couple times. I could even add some more in here, right? So it'd be easier for you guys to see it, right? It's just water. Right? It's just water. Now, the more water I add, the less of a color change, because it won't be red, it'll be pink, or right? But it's fine. Okay, so we've got the initial reading, we've got our analyte already, and then you're supposed to add it slow or fast. Yeah, usually, if you have a whole lot of unknown, do this first one fast, because then you do the next one slow. You end up saving a lot of time. Otherwise, you're sitting here going, oh, know, drip, 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 right? And then you're stirring it to see if the color will go away, right? Because you can see it. I don't know if you can see it, but if I add some, you see the color in there already? Do I quit? No. So it's best. So we'll just do the first titration here, but all right. But notice how the color goes away right away, right? So how does it know to change color? pH. What does the pH have to do with anything, though? Let's go back. This is why it works. When all of this, my analyte is an acid. When all of that analyte reacts, I'm going to add one drop too much of the base. That pH is just going to skyrocket because all that acid's reacted. What you're really doing is, notice how you're adding, I can't point that high. Where's my pen? All right, this is supposed to be, yeah, here it is, volume of NaOH. You're adding base. But is the pH changing? This is pH. You're adding base. But the pH, is it changing? No. This is a what? This solution starts with B. It's a, we haven't talked about it yet. It's a, what's the name of a solution that doesn't change pH? You keep adding acid or base. It's a buffer. We haven't talked about buffers yet. But this is a perfect definition of a buffer. Look at all the base we're adding. It's not changing pH. So, and we're going to see that's really what's happening. Is you keep adding more and more base here, more and more by titrant, the pH isn't changing. What's reacting with the base? My analyte is. That's why the pH isn't changing. The analytes react. Every little drop of NaOH I add, the acid reacts with it. So it keeps the pH the same, right? If I add more analyte, it's just going to push this change out further, right? Well, this require more base. If I add more analyte, it won't change anything with it. So I got to keep adding this until finally all of my what reacts? Analyte. As soon as all that analyte reacts, I'm going to add one drop too much of this stuff. The pH is going to change like a rocket because there's nothing left to react with it. And that would be pretty much right around here. So keep on adding, keep on adding. Yeah, I should get Danielle up here to turn that knob. Danielle, why don't you do that? You turn that knob. I'll stir it while you stand over here so people can see it. Or you stir and I'll do the knob thing.
Okay.
Dang. Ooh, did we go too far? Oh, we are really close. We did. We probably went too far, right? Because it won't go away. But so we just got it. So we know that, what is it? 20. I can't read that. Oh, there it is. It's 35 point, I'd say like 9, right on the 9, 35.9. .9. So that's about, what, 0.5, about 21.5 about? Is that right? So what was the equivalence point, end point? When this guy changed color, if we could have gone a lot slower, right? Are we talking about which one of these? End point. End point's what you see in the lab. Then what's the equivalence point? What's the equivalence point? The equivalence point is theoretical. So you have to know what the right answer is to get the equivalence point. In other words, well, we could do it this way. 21, well, yeah, equivalence point is a mathematical one. Think of it that way. That's the best way to think of it. Equivalence point is a mathematical one. Endpoint is what you observe in the lab. All right? Well, how do you get the mathematical one? All right? To me, I think it all starts right here. They should be the same, right? In theory. Yeah, that's a good point. These guys should be the same, but they're not, and that's what this is all about, titration error. But first, let's get through this first. Okay, we have 21.5 mils of 2.1 molar NaOH equals 10 mils of we don't know how much molar HNO3. So that's chemically the same. There's 21.5 mils of the 2.1 molar NaOH. That's so much NaOH. Right? Well, how much HNO3 does that equal? All right? You can kind of think of it as moles of NaOH has to equal moles of HNO3, at the equivalence point. Mm-mm. It looks like it, doesn't it? Doesn't it look like you do MIVI, MFVF? No. You're going to... In fact, I think it might work when it's 1-to-1. But I wouldn't, right? I wouldn't take the chance. So I would just work it out like we normally do. First, we're after the unknown molarity of HNO3. And we know molarity is what over what? Moles over liters. Okay, we already know the liters part, right? That HNO, we already know the liters part. That's how much did we titrate? How much of this stuff? Because we're looking for the molarity of the HNO3. What's the volume of it? 10 mils, which is 0.01 liters. Right? So this guy is 0.01 liters. The only part we need to figure out is the moles of HNO3. Right? So let's do that. All we're going to do is, can you see this right here? If you look at this, do you see moles of NaOH? You know the volume of it? You know its concentration? This is really moles of NaOH. And then you use the, what do we call it? The what bridge to convert it into moles of HNO3? The mole bridge, right? You need a reaction, right? And then we'll use the mole bridge in that reaction, the ratio, to go into moles of HNO3, and we'll have it. So start with the 21.5 mils of that NaOH, 1,000 mils in a liter. That 2.1, the 2.1 has to go on top, right? Because it's moles of NaOH. All right. So all I'm doing is I'm finding out the number of moles of NaOH. That's all I've done so far. The volume of that NaOH that I added, converted into liters, times the concentration. Now I need my mole bridge, which is really just, we could write the reaction, but is it going to be 1-to-1? Yeah, because all you're really looking at is this acid. Is it monoprotic, diprotic, triprotic? It's only monoprotic. So that means one NaOH, one OH is going to react with every H, or one NaOH is going to react with every one HNO3. So it'll be 1-to-1. Well, you could finish this if you want to see a complete reaction. Okay. Oh, hey, let me see if I can confuse you. This is the reaction that's happening. So we ended up with making some water and some sodium nitrate. Well, why don't we see a hunk of solid in here? Some sodium nitrate. Yeah, they're soluble. They're spectator ions, right? That it's a salt, but it dissolves in water, so you're not going to see it. Okay. So 1-to-1. And we end up with, oh my goodness, let's see, 21.5 divided by 1,000 times 2.1, 0.045. So he's 0.045. So divide that by 0.01. You get about 4.5. So my my concentration of HNO3 is 4.5. I had put the 0.045 here. I had to divide it by the 0.01 liters. We could have gone all the way to grams of HNO3. That's what this lady was interested in. She wanted to know if she had 90 nanograms or more. She didn't care about concentration. So we could have gone to grams of HNO3 if we wanted, but the question was interested in molarity of HNO3. Okay. Are you okay so far? I got 4.5 big M. So I divided 0.045 moles by 0.01 liters. And then I got the 4.5 molar. Yeah, you got to divide it by the volume. Okay. Now, somebody brought up an interesting point. These two aren't necessarily the same thing, right? I mean, we could have started with the exact right answer of the HNO3 and converted that all the way to volume of NaOH. In fact, I think you're going to have to do that in lab to help prepare. And you may have come up with, I don't know, what number did we end up with titrating? 21.5. Maybe theoretically it's 20 or something, right? There's error here. So we're adding this NaOH. It reacts with the analyte, the HNO3. Did it react with the, what do we call this? Did it react with the indicator too? Yeah, it did. This is an acid. You're adding an acid to titrate another acid. I mean, yeah, right? So you're going to be off. So you might, when you do titrations, don't be squirting a lot. Ooh, nice big pretty colors. You don't want to use a lot. Or you don't care if you just add the same number of drops for everything, right? Just always use the same number of drops. If you want to use 10 drops, fine, but stick with 10 drops for everything, right? But still, it's error. And what you could do to take it into account, and another error, it may not seem like it, because we said that, here's my water, we said that I was just adding pure water, right? Is that really the case? The only way you know this is what's the source of this water? It's a DI water, which comes from a deionizer, which comes from upstairs. The only way you can answer this question is if you know how that thing works. That deionizer has to take all the what out of the water. That's its goal. Ions. The deionizer takes all the ions. Oh, what ions are there? What's that? Like what? Some hints. Oh, iron's in there, but not a whole lot. Because there's going to be a lot of iron in your water if you get all those red stains. We don't really have that problem, do we? There's some fluoride, but not a whole lot. Yeah, all that. Hard water. When they say hard water, they're referring to what ion? Calcium. Right? There's some calcium. There's some carbonate. But there's not a whole lot. But it's healthy water. If you drink this stuff all the time, you'd be leaching that stuff, that good stuff, out of your body. The calcium, because right, it's diffusion. So you shouldn't drink the eye water. Okay, but let's get back to the point here. It kicks out, it gets rid of these ions, calcium, some fluoride, but not a whole lot. It's mostly calcium that we're worried about. And not iron really in San Antonio either, mostly calcium. Well, how does it do it? Anybody know? How does it do it? It's not a vacuum cleaner or anything. It's not a little, they don't have, it'd be nice if they had this, an engineering type of filter where calcium can't fit and only water could. That would be nice, but we don't have it. It'd be nice if we had something like that, but it doesn't exist. Now, there's these guys that say it works. You can go to Lowe's or whatever. I mean, it's not Lowe's is pretty good. I don't think they sell this, but go to Dollar General, right? And they sell this huge-ass magnet that you can put on your copper pipe, right? It doesn't work. deionizer. What it does is, some folks helped me change a cartridge. Who helped me? Someone did. Right? Okay. Do you remember going up there? We popped these big long filters off. I don't know if you looked in there, but there's these little tiny orange beads. And in these little tiny orange beads they're coated with sort of a gel. And all it is they call it cation exchange. And all that happens is it has a real affinity. It sucks up, it likes calcium. Great. But when the calcium comes in, hydrogen ions come off. So all it is, it's replacing every single metal with hydrogen ions. So when we added this, yeah, there's no ions in there, but it's a little bit acidic. It's a little bit acidic. Not a whole lot, but if you stick your little pH electrode in here, it would be above 7 or below 7. Below. It should be 7.00, but it's not. It's a little bit below because it's a little acidic. And that's why there's this titration error, right? And if your life depends on it or someone's prescriptions depend on it, because this is a very cheap way of finding out the amounts of things, you want to figure out what this error is. You want to know how much, like we added, what was our number, 21.5. Well, not all of it went into HNO3. Some of it went into reacting with the hydrogen ions that are here, reacting with the indicator. How could you find out the amount? If you knew it was 1 mil, then we wouldn't use 21.5, we'd just use 20.5, right? How would you figure out that titration error, that 1 mil? Just do a blank titration. Get a beaker, right? Nice clean one. You dump in the same amount of water that we used for this guy, dump in the same number of drops of indicator, and titrate them. It's not going to require much, but it will require something. A half a mil, depends on how big the error is. And then you subtract it from this. Okay, think of it this way. All of this NaOH that we just added, right, we used it. And we said this mils of NaOH is equal to this amount of HNO3. Not true, because some of that NaOH was used to titrate it sounds weird to titrate water, but there's acid in here because of the deionizing process. So it's a very small amount, though, because there's not a whole hell of a lot of calcium in there, right? You look at all the gallons of water that have to come out of this for you to even get a little bit of calcium. And there's micrograms there. There's not a whole lot, but it's there. And then the indicator itself, too. So you have a couple things where this NaOH isn't reacting with just the HNO3. It's also this other stuff. So this number is really a little bit too high. So how do you figure out how much to subtract? Do a blank titration. Do a titration that you use the same amount of water you just used. Because I remember I dumped in a whole bunch. Well, this you can't dump. You're going to have to measure it. You can still dump, but just know how much you dumped. Know how many drops of indicator you used. And then titrate that. You call it a blank titration. No analyte, exactly. There you go. Perfect. Everything but the analyte. And then you subtract it from the 21.5. Yep.
Wait, but so what are you measuring then? Like, it's just your...
No, your indicator's in there. You'll know when to quit.
Oh, okay, so it's still going to change even if there's no...
Yeah, and you should probably save this solution so you can match colors, right? Okay. Yep. It all still works. There's titrations that aren't in water. You still do blank titration. Might even be more important because maybe your solvent is interacting with your titrant. Mm-hmm. Okay. Well, then you would just titrate those. So what you'd have to...
No, we didn't use the analyte. I'm sorry, we used the titrant. That's what it was. Never mind.
You okay?
Yeah.
So... Okay. Okay.
We let out 20 milliliters. Right. We decided with the tritone.
Okay. Spectrophotometric titration. Spectrophotometric titration. We're still going to plot the mils of titrant, whatever's in the burette, but now you're just going to monitor color, right? So I don't know. I guess you'd stick this whole thing in like one of those little Spec 20s, or just keep dipping it out and putting it in there. It'd be a lot easier to have a little probe in there that sits there and monitors the absorbance all the time. That'd probably be a lot easier. So you're just plotting it versus absorbance. But it's absorbance, transmittance, something that has to do with spectroscopy, percent transmittance, and you end up with the same thing if it's monoprotic. But now, before, we're titrating, and then I get a drop on the side. Like, well, that's a good example. See what's right there? Ah, shoot. Right? You can go like this. You don't care. But you can't do that with this. Do you see why? Because if you all of a sudden add some water, you're changing the absorbance. You're changing the transmittance, right? It's kind of like if I add a bunch of water to this, I'm not adding any titrant. My signal is going to change big time because this stuff is going to become much more dilute. It's going to be more pinkish, a lightish color. This absorbance is going to drop. My signal is going to drop. It's going to look ugly. It's not going to look like this at all. It's going to go whoop, whoop. It's going to look, right? So you can't be adding water during a spectrophotometric titration. Okay. So here's a bunch of questions. Okay, let's see if we can set them up. And then you can always finish them at home or something. But how many mils of 0.1 molar, or sorry, how many mils of 1 molar Ki are needed to react with 40 mils of 0.04 molar mercury nitrate? I think that's mercury 1 nitrate. If the reaction is mercury 1 and 2 iodides gives mercury iodide. Okay. Yeah, there's our mole bridge right there. Here, we can use all these ratios. We're going to need those. We want to end up in mils of Ki. Where would you start? Start with the 40 mils of the 0.04 molar. If you don't quite see this, start with this stuff, then what you should do is, that's why I wrote, let me clean this up a little bit. That's why I wrote this. Because that's what titrations are. Something is chemically equivalent to something else. And if you can see that in the word problem, it's so much easier to read. They're saying that this stuff is chemically equivalent to this stuff, right? You're going to convert one thing to the other. 40 mils of the mercury nitrate equals, I don't know how many mils of the 1 molar Ki. Okay, so you could start here, or you could start like how we did previous problems. It's going to be the exact same thing, because what are the units of my answer? Mils of Ki. And where do you see that up here? Yeah, but right here. You could start with this guy, but flip them. That would work too. And you just keep playing that game we did before, canceling units to get to your right spot. But since this is the titration, and we're using mole bridge and things, it seems like it's more logical to start with the chemical equivalency idea, that 40 mils of this compound is equal to how much of this compound. So you start with what you know. But you don't have to. You can start with this guy and flip them. But I'm going to start here because I want to convert to mole. Because if they tell me volume and concentration, I know moles. And then it's logical. I know the moles of this stuff. Use the mole bridge to get in the moles of the other guy. And then I can get into volume. It just seems more logical to me. So I'm going to do it that way. I'm going to start with the 40 mils and convert that to right, 40 mils, 1,000 mils in a liter. Now I would do what? That Hg2NO3, the 0.04 molar of it, right? Yeah, and the liter has to be on the bottom. And I don't really need to write this whole big formula. All I'm really interested in is what? Hg2 plus 2, right? So that means this stuff must be spectator ions. All I'm interested in is that Hg2 plus 2. And then you molar bridge it, right? And I want to get into moles of, using the mole bridge, I want to get into moles of what? Ki, but that's not up here. Moles of I. Yep, I and Ki, the same thing. And the ratio is 2 to 1. Exactly. Okay. Now I can keep going. I'm ready for this one. If you're not comfortable seeing Ki being the same as I, no problem. You can just write in 1 mole of I have 1 mole of Ki. They're the same thing. If if you're not comfortable writing the concentration right away, it doesn't hurt anything. All right, now we have 1.00 moles of Ki in a liter of that stuff. And then they want it in mils, so, right?
So we technically didn't even have to put in the first.
You don't need this guy at all, no.
The first
So basically, the liters were canceled.
Yeah, they did, didn't they? Yeah. Yeah. Okay. Now here, this is a good one where MIVI, MFVF would not work if you accidentally used it, because that mole bridge would really screw you over. Limestone consists of calcite. The carbon content of 0.5413 grams of powdered limestone was measured by adding 10 mils of HCl and heating. Okay. So you added some HCl, right? And it reacted with the calcium carbonate, right? By this reaction right here. Okay? But you must have added way too much because, right, there's some left over that reacted with this stuff. Okay? No, no. The only time you can do MIVI MFVF is dilution, right? Pull that totally out of your brain. You're not going to see it. I'd say ever. Okay. All right. So you got picture this though. Let's start with what they want. They want the weight percent of this calcite, right? Of calcite and limestone. Calcite is just that calcium carbonate. So just to write a little equation over here to show you what they want. The weight percent is going to be the grams of the weight percent of calcite. Now calcite is just calcium carbonate. So they want the grams of the calcium carbonate. And what's the total grams? All right? Because the weight percent of anything is the grams of the solute over the total grams times 100. Now we don't know the grams of calcite. That's going to be, we're going to find it. But what's the total grams? It's up there, 0.5413, and then times 100. Okay, so this is the big game plan right here. We just have to get the grams of this calcium carbonate. Okay. How we're going to get it is, well, mole bridge. We're going to need to use that mole bridge for sure. But do you see how the HCl that they added, this stuff, is, just think of it in terms of, whenever they give you a volume and a concentration, think of moles. You know the total moles of HCl. That's right here. You know the total moles of it. And it was divvied up between what two things, these moles of the HCl? They went where and where? Some of it reacted with that calcite. And then the rest reacted with the NaOH, right? So you could kind of write a little thing here. The total moles of HCl is going to, someone's going to have reacted with the calcite, calcium carbonate, the calcite, right? Then the rest reacted with the NaOH. So how do we get the total moles of the HCl? It's up there. They gave us the volume and they gave us the concentration, right? So by looking at this, hopefully you're getting comfortable thinking, I know the moles of HCl. I'll just convert the 10 into liters and multiply. All right, I'll know that. I know this. Everyone following me? Okay. The amount that reacted with the NaOH, can you see it? Can you see it? By looking at this, don't you know the moles of the NaOH? Is that the same as the moles of the HCl? Yeah. It's just because they're 1 to 1, right? Monoprotic acid's always the same. So the moles of NaOH is the moles of the HCl. What's left over is the moles that reacted with this. So you're going to solve for this. You can get moles of HCl. Now we use Adrian's mole bridge to get moles of calcium carbonate, convert it to grams. Okay? See the game plan? All right. So come by. I'll be glad to help you out with this stuff.